I think have I put it on the recording? Yes. Very good morning to one and all present here. Let me begin today's class with that we had done in the previous class. Okay. So let me start writing the problem. Solve the difference equation. Solve the difference equation. Okay, where y of n minus 3 by 2 y of n minus 1 plus 1 by 2 y of n minus 2, that would be equal to x of n. Okay, for n greater than or equal to 0 with initial conditions y of minus 1 equals 4 and y of minus 2 equals 10, and x of n would be equal to 1 by 4 power n u of n. Okay, so this is a problem related to a unilateral Z transform. One of your friend told me to solve this, and I'm just solving it, and I'm making half of the solution here. So how to substitute, and the remaining half of it, I think I can give to any one of them. They can do solve the given difference equation by partial fraction expansion method, and later on they can come to the solution. Okay, so that will not have much time. Okay, so that's the reason why I'll just give you the way in which it is to be solved. Okay, so the first step what we need to do here, whether to identify it is a unilateral Z transform. So how you are going to identify it? You are going to identify it whether the given difference equation needs to be solved by applying the unilateral Z transform or the conventional Z transform approach there. So for what you have to do here is you have to identify at the end where the n, whatever that has been given, it is greater than or equal to 0. It means that it is a unilateral Z transform which needs to be solved. So this equation here, which is y of n, let me write down here, y of n minus 3 by 2 y of n minus 1 plus 1 by 2 y of n minus 2, that would be equal to x of n, where the input x of n will be equal to 1 by 4 power n u of n. Okay, so now I have understood that I need to apply the unilateral Z transform. Let me apply the Z transform approach here. So Z transform of y of n, that would be equal to y of z. Okay, so that would be equal to y of z. So what you need to observe in the given equation is it is delayed by 1 unit, and this one which is delayed by 2 units there. So this one, it is delayed by 1 unit, this one by 2 units. Okay, so these are the two things that you need to observe carefully. Okay, and also the initial conditions, the value of it, right? So when n is equal to minus 1, y of minus 1, that would be equal to 4. Next, when n is equal to minus 2, y of minus 2, that would be equal to 10. So for n greater than or equal to 0, this is one thing that you need to apply or you need to keep in mind there. So most of you will go wrong. Okay, so you will just apply the Z transform here depending on the time shifting property, and then you will come. Okay, so please observe carefully that it is n greater than or equal to 0 there, then you are going to apply the unilateral Z transform. Okay, so let me apply the unilateral Z transform quite carefully. So Z transform of y of n minus 1. Okay, so recall it is a delayed sequence, so it is a time delay sequence. So how we are going to apply the Z transform for it? It is Z inverse y of z plus y of minus 1. Okay, so Z transform of y of n minus 2, that would be z power minus 2 y of z plus z inverse y of minus 1 plus y of minus 2. Okay, so these are the three things that you need to remember, and Z transform of x of n, so that would be equal to x of z. So that is Z transform of 1 by 4 power n u of n, that would be equal to z divided by z minus 1 by 4. Okay, so that is what you need to keep in mind, and you have to apply the Z transform analysis, okay, after using the tool of Z transform. So what would be the concern there? Okay, so y of -1, if I want to replace, that is Z inverse y of Z plus 4, that would be equal to Z power -2 y of Z plus Z inverse into 4 plus y of -2, that is 10. Okay, so I apply each and every term to the difference equation that is being given there. So y of n, that would be equal to, if I apply the Z transform, that is y of Z minus 3 by 2. Okay, y of n minus 1. So y of n minus 1, if I want to do it, I mean, if I want to replace it, that would be Z inverse. Okay, Z inverse y of Z plus, okay, Z inverse y of Z plus y of minus 1, that is equal to 4 then. Okay, next, what do I need to do? Plus 1 by 2 y of n minus 2. What is y of n minus 2 here? So that y of n minus 2 would be Z power minus 2, Z power minus 2 y of Z plus, okay, Z power minus 2 y of Z plus Z inverse into 4 plus 10. Okay, that would be equal to Z transform of x of n. The given x of n would be Z divided by Z minus 1 by 4. Okay, so how did I write it? I applied the Z transform for 1 by 4 power n u of n. Okay, a power n u of n. So a takes the value 1 by 4 there. So that's the reason why I applied the Z transform for the given input, say x of n. Okay, so from here onwards, you know it. So the first step, what you are going to do here is you are going to have y of Z term being present there. Okay, so y of Z term, you are going to write it and you are going to solve it. Okay, so the Z transform of this one, you already know that it is Z divided by Z minus 1 by 4. You are going to make the relevant substitution and you are going to get the y of Z in terms of the polynomial. Okay, polynomial and polynomial of numerator term and polynomial, okay, polynomial of denominator term there. Okay, so numerator term and denominator term will have the polynomial. So the numerator polynomial is said to be 0 and this one is said to be the poles. Okay, so from here you are going to have the partial fraction expansion method, the partial fraction expansion method, and then you are going to have the y of n term. Okay, so from y of Z you are going to take the inverse Z transform, that is y of n. Okay, so I'll give this problem to Chirantana. Okay, Chirantana, so you have to solve this problem and share the solution to the given problem in the group. Okay, so with this note, I would like to end the solution to difference equations problem that have been listed out in the given Z transform there. Okay, so next important topic that I would like to discuss is regarding the stability. Okay, regarding the stability and causality, regarding the stability and causality of the system. Okay, when it comes to Z transforms, okay, so how are you going to say that a given system, okay, so given it might be a transfer function, say h of Z. Okay, so h of Z, how you are going to define h of Z? H of Z is to be defined by y of Z divided by x of Z. Okay, so h of Z is the Z transform of the impulse response, that is h of n. So from h of n, it would be relevant to talk about the h of Z by taking the Z transform. So in order to take the Z transform, okay, so you need to have the transfer function. H of Z is also called as the transfer function. So that can be determined by taking the Z transform of the output signal divided by the Z transform of the input signal. Okay, so now y of Z is called the that is the zeros. Okay, zeros and x of Z polynomial. So both are in polynomial term, that is an algebraic equation in terms of Z. So the denominator term is called as the poles there. Okay, so now when I want to talk about the stability and the causality of the system of a given h of Z, okay, so one thing what it determines is the pole zero pattern. Very important concept here. So it will be asked definitely for your competitive exams, any competitive exams, as a matter of fact. Okay, so the Z transform approach, so how it is relevant to the stability and the causality of the system, comment on the stability, whether it is stable or not, whether either it might be stable or it is not non-stable, that is unstable system there. Okay, so it might be causal or a non-causal system. Okay, so when you consider both the system either to be stable and causal, so both the systems are not called as a stable or a causal system. Okay, so in that manner you are going to identify. Without the definition being properly known to you, you are not able to do that, or you will be finding difficulty whether to identify the given system is a stable system or a unstable system and so on, right? So one thing that you need to keep in mind is the pole zero pattern there. So pole zero pattern, so when I talk about the pole zero pattern, you have to remember that it is the zeros and the poles which are present there in the transfer function. Okay, so transfer function here refers to h of z. Okay, so the pole zero pattern and also the region of convergence, as I already told you, ROC. Okay, so the region of convergence of h of z determines the stability, and causality of the system. Okay, determines the stability and causality of the system there. So one thing, the first option is to find out the pole zero pattern. So second one is the region of convergence of h of z. Okay, so h of z here refers to the transfer function. Okay, so pole zero pattern determines the stability and causality of the system along with the ROC of the transfer function. So very important point with respect to the GATE, what I'm talking about here, the graduate aptitude test for engineers. Okay, so very important topic that needs to be discussed in today's class. It is better that you make a note of it, or definitely I will be sharing the videos and so on. Okay, so now if I want to talk about a system only to be causal, okay, so only to be causal and it is not stable. Okay, so when I talk about causal, okay, you need to remember that it is unstable system. Okay, so once I say the system is said to be causal, it is definitely going to be, when I talk about two different properties here, causality and the stability. So once I say when the system is said to be causal, and it is definitely a unstable system then. Okay, so now as I already told you, h of n is the impulse response. Okay, so depending on the impulse response of the system, we are going to determine whether the system is said to be causal or not. So h of n is the impulse response of the system. H of n is said to be the impulse response of the system. So h of n will be equal to 0 for n less than 0. Okay, so this is where you are generally calling the system to be causal. Okay, so if it satisfies this condition, okay, so condition, I'll write it here. So if it satisfies the condition, say h of n would be equal to 0 for n less than 0, that is this impulse response of the system will be equal to 0 for n less than 0. So then you are calling the system to be a causal system. Okay, so now the other one, it is the ROC of the h of z. Okay, so when I'm talking about the z transform of the impulse response of the system, so ROC will be, okay, ROC will be outside the outermost pole. Very important concept here. Okay, so the first condition what you need to check is h of n will be equal to 0 for n less than 0. I can call the system to be a causal system. Second one, it is the region of convergence of h of z, which will be outside the outermost pole. So I can look for this one when I talk about the z transform of the given system, that is h of n. Okay, so if I want to if I want to find out h of z where the outside the outermost pole, that is the region of convergence. For example, you are having z equals 1 by 3, okay, as one of the pole. Okay, so say, let me talk about the poles here. So z is equal to 1 by 3 and z is equal to, okay, 1. Okay, so mod z greater than 1. Okay, so this is the outside of the outermost pole. Okay, so once you plot it, so it will be 1 by 3 here and it is 1 here. So let me plot a circle like this, and mod z would be greater than or greater than 1. Okay, so that determines the region of convergence. Okay, so then you are saying the system to be a causal system. Okay, so definitely the h of n will be equal to 0 for n less than 0 there. Okay, so z is equal to 1 by 3 is one of the pole here, so z is equal to 1 here. So region of convergence will be the right-handed sequence there. Okay, so in case if it is the other way, okay, so it is said to be a non-causal system. Okay, so mod z, so in the given problem they will be specifically saying that for a given system I say that this h of z is said to be causal. Okay, so determine the region of convergence. Okay, so you need to take the outside of the outermost pole for saying the system to be a causal system there. So that's the reason why I say it to be a causal system. So I repeat it once again, h of n will be equal to 0 for n less than 0. You call the system to be a causal system. Okay, next, once I talk about h of z, I clearly specify the region of convergence, which will be outside the outermost pole there. Okay, so this covers the causality nature. Okay, so causal system, whether h of z is said to be causal or h of n. So in both the ways you can verify whether you can tell that it is causal. Okay, so once it is causal, you are saying it to be an unstable system there, or you can say it is a non-stable. Okay, so now stable. Okay, so stability or stable system is said to be a stable system. Okay, so now when I call about the stable system, its impulse response h of n. Okay, so it should be absolutely summable. Absolutely summable. Okay, so stable system or non-causal system. Okay, so stable and non-causal system. Okay, so stable or a non-causal system. So h of n is absolutely summable. Okay, absolutely summable. And here, okay, so h of z lies inside the unit circle. H of z lies okay, so inside, okay, inside the unit circle in the z plane. Okay, so these two are the conditions to be specified, whether it is calling to be, it is said to be a stable system or not. So let me talk about the z plane here. So you are having the real part and the imaginary part here. Okay, so this one, when I talk like this, okay, so let me take z is equal to 1 by 2 and z is equal to 1 by 3 there. Okay, so it should lie within the unit circle. So this is z is equal to 1. Okay, so now you are having one more system, one more pole called as 1.125. Okay, so you are not calling the system to be a stable system. Okay, so both the poles, okay, so the number of poles which are to be specified for a stable system is said to be within the unit circle. So when I say unit circle, what do you mean by unit circle in case of z plane? Can anyone let me know? What do you mean by unit circle? In case of z plane, so what do you mean by a unit circle? So unit circle is where the radius of the circle would be equal to 1 unit there. Okay, so that is where you are going to call the system. Okay, it's to be lying within the unit circle, then you are calling the system to be a stable system. H of n is absolutely summable there. Okay, so h of z lies within the unit circle, then you are calling the system to be a stable system, and h of n is absolutely summable, then you are calling the system also to be the stable system. Okay, so now next one, what I can talk here is whether it is stable or, okay, stable, sorry, it is not or, stable and causal. Stable and causal. Okay, so now the given system under investigation, okay, given system under investigation, so where it can be called as both stable as well as the causal system. Okay, so now the ROC must contain the unit circle, must include or contain the unit circle. Okay, so and it must be outside, and it must be outside the outermost pole, and it must be outside the outermost pole. Okay, alternatively, for a system to be stable and causal, all the poles must lie must lie inside the unit circle. Inside the unit circle. Okay, so inside the unit circle. Okay, so now when I say the system is to be stable and causal, ROC must contain the unit circle. Okay, and it must be outside the outermost pole. Okay, so mod z would be like, if I give z is equal to 1, z is equal to 2, and z is equal to 3. Okay, so mod z should be greater than 3, and it must contain the unit circle. Okay, so it must contain the unit circle. So once I say mod z greater than 3, okay, so its ROC will be the right-handed sequence. So z is equal to 1, z is equal to 2, and z is equal to 3 here. Okay, so 1, 2, and 3. Fine. So ROC must contain the unit circle. Okay, so next, all the poles must lie inside the unit circle to be called as a stable and a causal. So in here, okay, so you are saying the system is said to be mod z greater than 3, so ROC will be this one. Okay, so all the poles must lie inside the unit circle. You are not calling the system to be, you cannot call, it is not stable. Okay, so it is a non-stable and non-causal system. Okay, so in such cases you are saying the system to be not stable or not causal. So both the conditions have to be specified to call it to be a stable and a causal system. Okay, so in the case what I specified here, okay, in the case whatever I specified here, so all the poles must lie inside the unit circle, which is not satisfying the second condition there. So that's the reason why I say the system is said to be a non-stable or an unstable or a non-causal system and a non-causal system there. Okay, so you have to practice these properties which are related to stability of the system, causality of the system, and so on. So next, what we are going to discuss is regarding the numerical problem. So how it is going to be applied on the numerical problems. Okay, so the first problem goes this way: determine whether the system described below is causal and stable. Okay, determine whether the system described below is causal and stable. H of z, that would be equal to 2z plus 1 divided by z squared plus z minus 5 by 16. Okay, so h of z is a given transfer function. H of z is a given transfer function, that is h of z, that would be equal to 2 times, okay, z plus 1 by 2. So why I'm making this changes, okay, so if I take 2 common one, so it would be z plus 1 by 2. Okay, so now you need to factorize this and you will be getting z plus 5 by 4 and z minus 1 by 4. Okay, factorize this and you will be getting the poles. Okay, so this one here will give you the zeros, this one here will give you the poles. So that is the numerator term, which is expressed as a polynomial in z, will give you the zeros. Okay, so this term here, which will give you the poles there. So h of z is said to be the transfer function. So h of z being the transfer function, you can reduce it to this form. You will be having, okay, let me draw it. Okay, so zeros at 1 by 2. So this is 1 by 2 here, so I'll write it as a 0. So this is how I represent the 0 of the transfer function. So z is equal to minus 5 by 4. So once you equate it, so z1 will be equal to minus 5 by 4. This is pole 1. Okay, so this is pole 1. Okay, next this one is pole 2. Okay, z equals 1 by 4. Okay, so z equals 1 by 4 here. So 1 by 2, I think half of it is 1 by 4. Okay, so you'll be having one more transfer function here, that is 5 by 4, which will be minus 1.125. Okay, I mean 1.25 there, sorry, minus 1.25. Okay, so now whether to call this as a stable system or not. Okay, so recall it. Okay, the location of the poles is clear, so just plot it. I just plotted here minus 1.25, and this one here, okay, this one would be 1 by 2. Okay, so 1 by 2 as a 0. Okay, this one is 0. and this one here is the pole 1. So pole 1 and this one here is pole 2. Okay, so now what do? I plot a unit circle. So z is equal to 1 here, I plot a unit circle. Okay, so if I plot a unit circle like this, what would be the thing there? So this unit circle will not have z is equal to minus 1.25 there. So that's the reason why I can generally say that this is not stable. Okay, so I call the system to be not stable and non-causal. Okay, so not stable and non-causal. Hope you are getting what I'm doing here. So understand here carefully. So look at the statement, whatever I have discussed here. So ROC must contain the unit circle. Okay, so ROC must contain the unit circle. Okay, so there is no ROC and it must be outside the outermost pole. Okay, so to an extent it is satisfying the outermost pole. And if you look at the second statement itself, you can clearly come to a conclusion that all the poles must lie inside the unit circle, which is not possible. See, one of the pole is lying outside the unit circle. Okay, that's the reason. So you have to specify the reason here. So reason to be specified is one of the pole, okay, is lying. Okay, you have to specify the pole. So that is Z2 pole. Okay, Z1 or Z2. Okay, so it doesn't matter. I think it is Z1 here. Z1 minus 5 by 4. Okay, is lying outside the unit circle. Okay, so then I can generally say that the given transfer function is not stable and non-causal. Okay, so that's the reason why I can say this. Okay, so this is how you can specify the given system, whether it is stable or not, whether it is causal or not, and so on. Okay, so it can be clearly said that the given system is not causal and not stable. Okay, so you have to specify the reason very clearly, how to see that the given system is said to be causal, stable, both causal and stable there. Okay, so you have to clearly note down so what it needs to be done. Fine, so I'll give this problem to one of you, whether you can able to do this. Okay, to z inverse plus 1 plus, okay, so 14 by 8 z inverse, okay, z inverse plus 49 by 64 z power minus 2. Okay, so just solve it. Okay, so just solve it and let me know whether the system determine the system whether it is stable and causal. Okay, so looking at the poles itself, you can come to know that whether it is stable and causal then. Okay, so see to it that you are going to solve it and you are going to find out whether the given system is said to be stable and causal. You have to prove both the things here. So whether it is stable and causal there. Okay, so third one, you can give a try, or else I'll send you the solution in detail. LTI, discrete system, a linear time invariant discrete time system. Okay, discrete time system. Okay, time invariant, generally I can call this to be a discrete system only. Okay, not a problem. Okay, is given by the transfer function, say h of z, that would be equal to 3 minus 4 z inverse divided by 1 minus 3.5 z inverse plus 1.5 z power minus 2. Okay, specify the ROC for h of z and determine h of n for the following. Okay, so for the following conditions. Okay, so first condition here, system is stable. Okay, so here we are saying the system is said to be stable there. Okay, so you have to specify it properly. You have to read the statement of the h of z say it to be a stable. Then only you can come to a conclusion that how the system, I say that this system is stable. So how we are going to determine what is h of n? Okay, so determine h of n for the following conditions. First one, the system is stable. Second one, system is causal. Okay, system is causal. Okay, so you have two things to be specified here. So first one, system is stable. Second one, system is causal. Okay, so these are the three things that you need to know. First one, you have to specify the ROC for h of z. So you have to determine h of n for the following conditions, that is system is said to be stable, and second one, the system is said to be causal there. Okay, so you have to perform these things. Okay, I think I have not got it with this. So this one I'll give it to Tanu L. Okay, so this one I'll give it to Tanu L. Okay, Tanu L, if she is not there in the meeting, just inform her. Okay, so third one I'll give it to Nishana. Okay, so I'll give it to Nishana. She can be able to solve it and understand how it is being done. Okay, so these two problems are to be done by today, and you have to like post it in the classroom group. Okay, so that is there. Okay, so see to it that you are going to solve it without any such help. Just look at the conditions, whatever that is being specified. Okay, so if you go wrong here, it is fine. Okay, so see to it that you are going to solve it. Take many number of attempts as much as possible. Verify what it is to be done, and if you are finding it difficulty, okay, so see to it that you are going to reach out to me anytime. Okay, so and solve the given steps. I mean, use the conditions which is to be specified, and you can just solve it. Okay, so see to it that you are going to solve very carefully and give the solutions. Okay, so with this note, I would like to just